Jupiter has no surface. If you fell toward it, you'd never stop falling. Not because the planet is infinite, because there's no boundary between atmosphere and interior. Pressure increases gradually, kilometer by kilometer, until hydrogen becomes metal and your body stops being solid. There's no impact, no moment of contact, just continuous transformation until the concept of falling stops meaning anything. This isn't a feature other planets share. Earth has a surface. Mars has a surface. Even gas giants like Saturn have detectable phase transitions. But Jupiter is structured in a way that makes the question, where does it end? Unanswerable. The planet doesn't complete processes. It suspends them. Matter enters states that physics describes, but cannot cleanly define. And that ambiguity isn't limited to Jupiter's interior. The same gravitational influence that eliminates boundaries inside the planet has been eliminating boundaries across the solar system for 4.5 billion years. Jupiter doesn't just exist in the solar system. It shapes it, violently, continuously, without resolution. This is the story of a planet that defies the concept of completion, a world that generates more energy than it receives, a gravitational architect that may have destroyed planets to create the system we inhabit, and why the most important question about Jupiter might not be what it is, but what it prevents from being. Jupiter is the largest planet in the solar system, 318 times the mass of Earth, more massive than all other planets combined. It orbits the Sun at 5 astronomical units, far enough that sunlight takes 43 minutes to reach it. And despite that distance, its gravitational influence extends across billions of kilometers, bending the trajectories of comets, asteroids, and the orbits of neighboring worlds. But Jupiter's dominance isn't just gravitational. It's structural, thermal, magnetic. The planet radiates more heat than it receives from the Sun, an internal engine that's been running since formation, powered by mechanisms science still debates. Its magnetic field is 20,000 times stronger than Earth's, trapping radiation in belts so intense they'd sterilize any spacecraft that lingered. And beneath the visible atmosphere, models predict phases of matter that exist nowhere else in the solar system. Yet we've never directly observed them. The deeper we look, the less Jupiter resembles a planet. And that uncertainty begins with the most fundamental question. Where does Jupiter's atmosphere end and its interior begin? Jupiter's atmosphere doesn't transition into a surface. It transitions into itself. At the cloud tops, hydrogen and helium exist as gases, thin, cold, familiar. Descend deeper, and pressure begins to rise. 1 bar becomes 10. 10 becomes 100. The temperature climbs past the boiling point of water, then past the melting point of lead. But there's no ground beneath. Just more hydrogen, denser, hotter, pressing in from all sides. At roughly 1 million bars of pressure, about 3,000 kilometers below the cloud tops, hydrogen stops behaving like a gas and begins behaving like a metal. Electrons separate from atoms. The substance becomes electrically conductive. It's still hydrogen, chemically identical to the hydrogen in Earth's atmosphere, but its physical state is so alien that calling it gas or solid becomes meaningless. It's a fourth state, one that only exists under conditions too extreme for direct study. This isn't a surface in any recognizable sense. There's no boundary you could stand on. No moment where atmosphere ends and planet begins. The transition is continuous, a gradient of pressure so smooth that defining where one phase stops and another starts is arbitrary. You could fall through Jupiter's atmosphere for hours, days, if your body somehow survived the heat and pressure and never encounter a moment of impact. Just steady compression until the hydrogen around you becomes indistinguishable from the hydrogen inside you. Scientists call the region below this transition the interior, but the term is conceptual, not observational. No probe has ever reached it. No instrument has ever directly measured it. Models suggest a core, possibly rock and ice, possibly 10 to 20 times Earth's mass. But even that remains unconfirmed. The core might exist. It might not. The planet's gravitational field is consistent with either possibility, which means Jupiter might not have a center in any meaningful sense, just pressure increasing without resolution. There's something deeply unsettling about a world where processes don't complete, where matter doesn't find rest. On Earth, objects fall until they hit the ground. The journey has an endpoint, but on Jupiter, the endpoint is transformation without arrival. You'd fall until you stopped being you. And even then, the pressure would continue, deeper and deeper, into states of matter we can describe mathematically but never touch. A planet where the concept of inside becomes ambiguous the moment you try to define it. But the absence of a surface isn't the real problem. The real dominance of Jupiter isn't written into its interior. It's written into the orbits of everything around it. Because Jupiter doesn't just exist in the solar system, it shapes it, and the evidence suggests it's been doing that violently since the beginning. Planetary formation is supposed to be relatively orderly. Dust aggregates into rocks. Rocks collide and merge. Over millions of years, gravity pulls material together until planets emerge, orbiting in roughly stable positions around their star. The story is gradual, predictable, controlled. But when scientists model the early solar system with Jupiter included, the simulations don't show order. They show chaos. Jupiter likely formed within the first few million years of the solar system's existence, early enough that the protoplanetary disk was still rich with gas and debris. And once it reached sufficient mass, its gravity didn't just clear its own orbit. It interfered with everything else. Models suggest Jupiter migrated inward, dragging closer to the Sun, pulling smaller planetesimals with it or flinging them into unstable trajectories. Some were ejected from the solar system entirely. Others collided with the Sun. A few may have crashed into the inner planets, delivering water and organics, or obliterating whatever was forming there before Jupiter's influence arrived. Then something stopped the migration, possibly Saturn, possibly resonance with other forming giants. The mechanics remain debated, but Jupiter reversed course, drifting back outward and stabilizing at roughly its current distance. That outward migration likely scattered what remained of the inner protoplanetary material, preventing a larger planet from forming where the asteroid belt now orbits. The belt isn't a planet that broke apart. It's a planet that never had the chance to coalesce, because Jupiter's gravity kept disrupting the process. This isn't speculation. It's extrapolation from orbital mechanics and asteroid composition. The asteroids in the belt show chemical diversity inconsistent with formation in a single region. They're fragments from across the early solar system, mixed and scattered by gravitational interference. Jupiter didn't just shape its own orbit. It rearranged the architecture of everything closer to the Sun, including, potentially, Earth. If Jupiter hadn't migrated outward, Earth might not exist. Or it might exist as something unrecognizable, a planet with 10 times the mass, or half the water, or no stable orbit at all. Our world may not be the result of orderly accretion. It may be the byproduct of instability that, by chance, stabilized. A side effect of Jupiter's gravitational dominance that happened to allow life instead of preventing it. And that dominance didn't stop in the past. Jupiter's gravity is still interfering, still bending trajectories, still acting as both shield and threat to every object that crosses its influence. Because the same force that reorganized the solar system 4 billion years ago is still operating today. And predicting what it will do next is harder than it looks. For decades, Jupiter has been called Earth's protector, a gravitational shield deflecting comets and asteroids that might otherwise collide with the inner planets. The logic is elegant. Jupiter's immense mass attracts objects crossing the outer solar system, capturing or ejecting them before they reach Earth. It's a comforting narrative, a cosmic guardian standing watch at the edge of the habitable zone. But the mechanics are more complicated and more unsettling. Jupiter doesn't just deflect objects, it redirects them, sometimes outward into interstellar space, sometimes inward toward the Sun and toward Earth. Gravitational assists work in both directions. An object passing Jupiter can gain enough velocity to escape the solar system entirely, or it can lose velocity and fall into an orbit that crosses Earth's path. The difference depends on trajectory, timing, and angles measured in fractions of a degree. This has happened. Observably, comet Shoemaker-Levy 9 didn't collide with Jupiter by accident. It was captured by Jupiter's gravity during a close pass, locked into orbit, and then torn apart by tidal forces before impacting the planet in 1994. The impact sites, dark scars larger than Earth, remained visible for months, a demonstration of Jupiter's capacity to destroy objects that come too close. But if Shoemaker-Levy had passed Jupiter at a slightly different angle, it wouldn't have been captured. It would have been redirected, possibly toward the inner solar system. The asteroid belt exists in its current form partly because Jupiter prevents it from coalescing, but also because Jupiter occasionally perturbs objects out of stable orbits, sending them tumbling through the inner planets. The same gravity that clears Jupiter's orbital neighborhood also populates Earth's. Every near-Earth asteroid that crosses our orbit is there, in part, because Jupiter's influence either nudged it inward or failed to eject it outward. Protection and threat aren't separate roles. They're the same gravitational mechanics, viewed from different outcomes. Scientists can model these interactions statistically, but they can't predict individual events with precision. Whether a given comet will be deflected away from Earth or redirected toward it depends on variables too sensitive to fully map. The solar system is stable, but stability here doesn't mean safety. It means the chaos has settled into patterns we've survived so far, patterns that Jupiter maintains not through deliberate shielding, but through sheer gravitational dominance that sometimes protects and sometimes endangers, depending on geometry we can't control. Earth's safety isn't guaranteed by Jupiter. It's negotiated by it. Every orbit, every close pass, every object that crosses Jupiter's influence represents a recalculation of risk we didn't choose and can't revise. And the most extreme demonstration of that power isn't written in Earth's orbit. It's written in the moons trapped in Jupiter's grip. Jupiter has at least 95 known moons. Most are captured asteroids, small, irregular, orbiting at vast distances. But 4 of them are different: Io, Europa, Ganymede, and Callisto, the Galilean moons. Large enough to be planets if they orbited the Sun independently, and locked in orbital resonances so precise that their positions repeat in mathematical patterns every few days. This isn't stability, it's entrapment. Io is the most volcanically active body in the solar system, not because it has internal radioactive heat like Earth, because Jupiter's gravity is tearing it apart. As Io orbits, the gravitational pull from Jupiter and the other Galilean moons stretches and compresses it, generating friction in its interior. That friction produces heat, enough heat to melt rock, enough to drive hundreds of active volcanoes across a surface that's perpetually resurfacing itself. Io doesn't have time to cool. The forces acting on it are relentless. Europa's surface is frozen water ice. Smooth, cracked, relatively young. Beneath that ice, evidence suggests an ocean, liquid water, possibly tens of kilometers deep, kept from freezing by the same tidal heating that destroys Io. It's one of the most promising environments for life beyond Earth. But Europa also sits inside Jupiter's radiation belts. The surface receives radiation doses high enough to sterilize organic molecules within hours. If life exists on Europa, it exists beneath the ice, shielded by kilometers of frozen water, surviving in an ocean heated by gravitational violence it can't escape. Ganymede is the largest moon in the solar system, bigger than Mercury. It has its own magnetic field, the only moon known to generate one. but that field isn't strong enough to shield it from Jupiter's radiation. Callisto, the outermost Galilean moon, sits just beyond the worst of the radiation belts. Its surface is ancient, cratered, geologically dead. It's the least affected by tidal heating, and it's still subjected to radiation levels that would kill a human in hours. These aren't habitable worlds in any comforting sense. They're environments where the conditions necessary for life, liquid water, chemical energy, geological activity, are produced by the same forces that make survival nearly impossible. Tidal heating keeps Europa's ocean liquid. It also ensures the moon can never escape Jupiter's gravitational grip. The radiation that sterilizes surfaces is generated by Jupiter's magnetic field, trapping charged particles. Habitability and lethality aren't separate features. They're consequences of the same system. If life exists on Europa or Enceladus or any other icy moon, it exists because of violence, not despite it, because a giant planet's gravity is strong enough to generate heat from tidal friction, because that heat persists even in the coldest regions of the solar system, because life, if it's out there, may depend not on refuge, but on being caught in forces it can't escape. Forces that, on a planetary scale, look less like protection and more like prolonged destruction. And all of this, Jupiter's moons, its gravitational dominance, its capacity to heat worlds through tidal forces, exists because Jupiter failed to gather just a little more mass, failed to ignite fusion, failed to become a star. Jupiter radiates more energy than it receives from the Sun, roughly 1.7 times more. That excess heat isn't leftover from formation, not entirely. It's being generated now internally, as the planet slowly contracts under its own gravity. The process is called Kelvin-Helmholtz contraction. As Jupiter shrinks imperceptibly over millions of years, gravitational potential energy converts to heat. The planet is, in effect, an engine, one that's been running since it formed and will continue running for billions of years more. This is a characteristic of objects that almost became stars. Brown dwarfs do the same thing. They're too small to sustain hydrogen fusion, but large enough to contract and generate heat from that contraction. Jupiter is smaller than a brown dwarf, by roughly a factor of 13 in mass, but the mechanism is identical. It's not a star, but it behaves like something that wanted to be. Compositionally, Jupiter is nearly identical to the Sun, roughly 90% hydrogen, 10% helium, with trace amounts of heavier elements. If Jupiter had accreted just a bit more mass during formation, if the protoplanetary disk had been slightly denser in its region, or if migration had brought it close enough to sweep up more material, it might have crossed the threshold for deuterium fusion. Not full hydrogen fusion, but enough to glow faintly in infrared, enough to be classified as a brown dwarf instead of a planet. It didn't. The mass threshold for deuterium fusion is roughly 13 times Jupiter's mass. Jupiter stopped growing at roughly 318 Earth masses, which means the solar system might not orbit a single star. It might orbit a star and a failed star, one that never ignited, but still dominates the gravitational and thermal architecture of everything nearby. The distinction between planet and star isn't clean. It's a gradient of mass, like the gradient of pressure inside Jupiter's interior. At some point, adding more mass changes the rules. But where that point is, and what it means for objects that sit just below it, remains conceptually ambiguous. Jupiter generates heat like a star. It has a composition like a star. It shapes its environment like a star. But it doesn't fuse hydrogen. So we call it a planet, and that label might obscure more than it clarifies. Because if Jupiter is best understood not as a large planet, but as a failed star, then the solar system's architecture makes more sense. The migration, the scattering of material, the tidal heating of moons. These aren't the actions of a passive planetary body. They're the actions of an object whose gravity rivals stellar influence, exerted across billions of kilometers, sustained across billions of years. An object that dominates not because it succeeded, but because it came close enough to failing that the difference barely matters. And that leads to the most unsettling implication: the stability we observe, the orbits that repeat, the moons that endure, the planets that haven't collided, might not be permanent. It might be a pause, a temporary equilibrium in a system still adjusting to the presence of an object that almost became something else. And whether that equilibrium holds depends on forces we describe mathematically, but don't fully control. Jupiter has no surface, no boundary between atmosphere and interior, no point where pressure stops increasing and matter finds rest. It's a planet defined by gradients of pressure, of phase transitions, of gravitational influence that extends far beyond its visible edge. And the deeper we look, the less it resembles the orderly picture of planets we were taught to expect. It migrated through the early solar system, scattering debris, preventing planets from forming, possibly delivering the water that made Earth habitable, or destroying whatever was there before. It radiates heat like a star that never ignited. It traps moons in orbital resonances that generate both the energy necessary for life and the radiation that makes survival nearly impossible. It deflects some asteroids away from Earth and redirects others toward it. Protection and threat aren't separate roles. They're the same gravitational mechanics producing different outcomes, depending on variables we can observe but not predict with certainty. And we call it a planet because it doesn't fuse hydrogen. But that distinction is arbitrary, a threshold of mass that changes the label without changing the behavior. Jupiter dominates the solar system not because it's a planet, but because it's massive enough to act like something more, something that shapes, disrupts, and sustains in ways that blur the line between construction and destruction. So what does that mean for the system we inhabit, for the orbits we occupy, the moons we study, the comets we track as they fall toward the sun or slingshot past Jupiter into interstellar space? It means stability isn't guaranteed. It's negotiated. Every orbit is a balance of forces that could shift. Every close pass of an asteroid represents a recalculation we didn't design and can't revise. The solar system is stable because Jupiter's influence has settled into patterns, but those patterns emerged from chaos, and chaos doesn't resolve. It pauses. We study Jupiter as if it's a feature of the solar system, but it might be more accurate to say the solar system is a feature of Jupiter, that everything closer to the sun, Earth included, exists in the configuration it does because a failed star 4 billion years ago migrated inward, then outward, and stopped at a distance where its gravity shaped planets instead of destroying them, where it generates heat without igniting, where it traps moons without consuming them, where it protects Earth from impacts, sometimes. And the question that remains isn't what Jupiter is, it's what it's still becoming. Whether the contraction will continue, whether the orbits will hold, whether the system we think of as stable is actually just a long, slow fall toward equilibrium we'll never witness. Because processes on Jupiter don't complete, they suspend. And maybe that's true for the entire solar system Jupiter dominates. If this changed how you see the boundary between planet and star, or the difference between protection and threat, consider subscribing. There are more questions waiting.